Bismillahirrahmanirrahim. Assalamu alaikum everyone. Well, introduce myself. My name is Mr. Bajwa. I am developer for BS Chemistry and my resource person Dr. Hammad Majeed. This is the second part of my presentation. First part, I have explained about basic knowledge of sodium azide. In this part, I will explain about sodium azide in reduction of chemistry. What is azide? Azide is an ion with the formula nitrite ion. It is a conjugate base of hydroxylic acid. Nitrite ion is a linear anion that is isoelectronic with carbon dioxide, isonate, nitrous oxide, nitrogen dioxide. Provalence bond theory azide can be described by several resonance structure and important one being azide is also a functional group in organic chemistry or N3. Preparation of azide. First, I discussing inorganic azide. Sodium azide is made industrially by the reaction of nitrous oxide with sodium amide in liquid ammonia as solvent. Inorganic azides can be prepared directly or indirectly from sodium azide. For example, lead azide used in detonators may be prepared from the metathesis reaction between lead nitrate and sodium azide. An alternative route is direct reaction of the metal with silver azide, dissolved in liquid ammonia. Some azides are produced by treating the carbonate salts with hydroxylic acid. Then I explain in organic azides. The principal source of the azide moiety is sodium azide as a pseudohalogen compound. Sodium azide generally displays an appropriate leaving group, for example, boron iodine to give the azide compound. Aryl azides may be prepared by displacement of the appropriate diazonium salt with sodium azide. Or trimethyl azide nucleophilic aromatic substitution is also possible. Even with chlorides, anilines, and aromatic hydrazines undergo dissociation as to alkyl amines and hydrazines. Appropriately functionalized aliphatic compounds undergo nucleophilic substitution with sodium azide. Aliphatic alcohols give azides by a variant of the Mistrobano reaction with the use of hydrozoic acid. Hydrazines being also from azides by a reaction with sodium nitrite. Reaction of azide. Azide salts can be decomposed with the releases of nitrogen gas. The decomposition temperature of the alkali metal azides are sodium azide to 75 degree, potassium azide 355 degree, rubidium azide 395 degree, and cesium azide 390 degree. This method is used to produce ultra pure alkali metals. Protonation of azide salt gives toxic hydroxylic acid in the presence of strong acid. Azide salt may react with heavy metals or heavy metals compound to give the corresponding azides, which are more shock sensitive than sodium azide alone. They decompose with sodium nitrite when acidified. This is a method of destroying residual azides prior to disposal. Many inorganic covalent azides, for example, chlorine, bromine, and iodine azides, have been described. The azide anion behave as a nucleophilic. It undergoes nucleophilic substitution for both aliphatic and aromatic system. It reacts with epoxides causing O-ring opening. It undergoes Mickel-like conjugate addition to one for unsaturated carbonyl compounds. Azides can be used as precursors of the metal nitrido complexes by being induced to release nitrogen, generating a metal complex in unusual oxidation state. Then explain reactions of azides. Organic azides engage in useful organic reaction. The terminal nitrogen is mildly nucleophilic. Azides easily extrude the atomic nitrogen, a tendency that is exploited in many reactions such as the Staudinger ligation or the Curtis rearrangement, or for example, in the synthesis of Y-amino B and amino esters. We have looked to the reaction of nitro ion. Azides may be reduced to amines by hydrolysis or with the phosphine, for example, triphenylphosphine in the Schrodinger reaction. This reaction allows azides to serve as protected initial synthons as illustrated by the synthesis of 1,1,1 trace aminomethyl ethane, lazide, alkyne, hexogen, cycloaddition. Organic azides react as 1,3-dipoxy reacting with alkynes to give substituted 1,2,3 triazoles. Another azide regular is twice azide her in reaction with norbornadians in a nitrogen insertion reaction. You have looked at the reaction of inorganic sodium azide. Thermochemical properties: delta HF naught 50.19 mole, delta GF naught 22.41 mole, S naught 23.15 mole, CP 18.31 mole. Preparation of sodium azide. Sodium azide is prepared by reacting sodium amide with nitrous oxide. The amide is heated with nitrous oxide at 200 degree or its solution in liquid ammonia is treated with nitrous oxide at ambient temperature. Uses of sodium azide. Sodium azide is used to make lead azide and hydroxylic acid and as the propellant for automotive safety bags. It also is used as an antihypertensive agent to control blood pressure. Physical properties of sodium azide. Colorless hexagonal crystals density 1.846 gram of centimeter cube at 20 degree, decomposes on heating to produce sodium, and nitrogen also decomposes in vacuum. Soluble in water partially, converting to hydroxylic acid. Solubility in water 41.7 gram over 100 milliliter. Slightly soluble in alcohol 0.316 gram over 100 milliliter at 16 degrees. Soluble in liquid ammonia. Analysis of sodium azide. Elements composition: Na 35.36%, nitrogen 64.64%. The salt is dissolved in water sufficiently diluted and analyzed for sodium. The solid powder is decomposed continuously and liberated nitrogen is measured by gas chromatography and mass spectrometry. The characteristic mass for N2 is 28. Hazard. Sodium azide is a toxic as well as an explosive substance. Although inert to shock, violent decomposition can occur when heated at 275 degree. Contact of solid or solution with lead and copper must be avoided. Reaction with halogens, carbon disulfide or chromyl chloride can be explosive. Dissolution in water produces toxic vapors of hydroxylic acid. The salt is an acute poison causing headache, hypotension, hypothermia, and convulsion. LD50 27 mg over kilogram. I want to explain in brimazide in front of you. Barium acetate also may be prepared by treating barium sulfide with acetic acid followed by show evaporation and subsequent crystallization of the salt from the solution. Reaction of barium azide. Barium acetate converts to barium carbonate when heated in air at elevated temperature. Reaction with sulfuric acid gives barium sulfate with hydrochloric acid and nitric acid. The chloride and nitrate salt are obtained after evaporation of the solution. It undergoes double decomposition reaction with salts of several metals. For example, it forms ferrous acetate when treated with ferrous sulfate solution and mercurous acetate when mixed with mercurous nitrate solution acidified with nitric acid. It reacts with oxalic acid forming barium oxalate. Barium analysis. Elemental composition: barium 53.77%, carbon 18.81%, hydrogen 2.37%, oxygen 25.05%. The salt may be digested with nitric acid diluted, appropriate, and analyzed for barium toxicity. The salt or its aqueous solution is highly toxic. LD10, rabbit 23.6 mg over kilogram, LD10, rabbit 96 mg over kilogram. Barium azide. Uses of barium azide is used in explosive. A saturated solution is generally used. Physical properties: colorless monoclinic crystals, density 2.936 gram over centimeter cube, decomposes at 120 degree, soluble in water, slightly soluble in ethanol. Preparation of barium azide. Barium azide may be prepared by reacting sodium azide with the soluble barium salt. The solution is concentrated to allow crystals grow. Crystals will explode if fully dried or subject to friction. Products should be stored damp with ethanol. Hazard: the dry solid is sensitive to shock, impact, and friction. It decomposes explosively when heated to 275 degree. Contact with acid can produce the barium azide compound hydrozoic acid. Contact with lead, silver, and many other metals can form the explosive azides of those metals. Presence of sodium, potassium, barium, and iron as impurities can enhance the shock sensitivity of barium azide. Barium azide also is a toxic compound. The toxic effects are similar to those of other soluble salts of barium. Lead azide. These basic acetates are used in the manufacture of pigments in dyeing and printing fabrics, the aqueous solutions in medicine for wash, and politicians in sugar analysis, and as starting materials for preparing other lead salts. The basic acetates are heavy white powders, decompose on heating, readily dissolve in water, and have low to moderately high solubility in ethanol. Preparation of lead azide. Basic lead acetates are prepared by dissolving lead monoxide in hot dilute acetate acid, or by dissolving the oxide in dilute acetic acid at alkaline pH. They may be made by dissolving lead monoxide in a solution of lead acetate. Crystalline products are obtained upon cooling the solutions. Analysis of lead azide. The composition of the salt is determined by elemental analysis, including that of lead and X-ray methods. The water of crystallization may be measured by grammetry. Uses of lead azide. Lead azide is used in fuses and detonators as a primary explosive to initiate the booster. It also is used in shells and triggers. Physical properties. Colorless needles are white powder, density 4.0 gram per centimeter per cube, explodes on heating at 35 degrees, slightly soluble in water, 230 mg over L at 80 degree, and 900 mg over L at 70 degree, while soluble in acetic acid, insoluble in ammonia solution. Thermal properties of lead azide. Delta HF naught 110.5 kilocalorie over mole. Preparation of lead azide. Lead azide is prepared by the reaction of sodium azide with lead nitride. Analysis. Elemental composition: 71.40 degree, nitrogen 28.86%. Lead azide is digested continuously in nitric acid, undergo mild heating. The solution is diluted and analyzed for lead by various instrumental techniques. Hazard: lead azide exploded on heating at 350 degree or on precautions. Its detonation velocity is 5.1 kilometer over second. It undergoes violent explosive reaction with carbon disulfide and forms shock sensitive copper and zinc azides. when mixed with the solution of copper and zinc salts. Cerium hydroxide. Preparation of cerium. Cerium hydroxide is obtained in industrial scale from monoxide sand PO4. In the laboratory, it may be prepared by treating caustic soda solution with cerium chloride followed by crystallization. Analysis of cerium. Elemental composition: cerium 73.30%, hydrogen 1.58%, oxygen 25.11%. The compound may be analyzed for cerium in aqueous phase by AA or ICP spectrometry after it is digested with nitric acid and diluted appropriately. Next, I explain in hydroxylic acid in front of you. Physical properties: colorless, volatile, liquid, pungent, disagreeable, odor, density 1.09 gram over ml, solidifies at 18 degree, boils at 37 degree, highly soluble in water, soluble in alkalis, alcohols and ether, 4.6 at 25 degree. Preparation of hydroxylic acid. Hydroxylic acid is prepared by reacting sulfuric acid with sodium azide, or by treating hydrazine with nitrous acid, or by heating sodium amide with nitrous oxide. Next, I explain hydrazine history and uses. Hydrazine drugs such as isoniazid are used extensively for treating tuberculosis. Other applications of hydrazine include its use in fuel cells and in wastewater treatments for removal of iron removal from hot water heating systems, reduction of red iron oxide rust into magnetic, and for removal of oxygen to protect against corrosion. It also is used in electrolytic plating of metals on glasses and as a reducing agent. Several hydrazine derivatives are used in azides as coupling agents in color photograph and in explosive and ammunition primer. Reaction: hydrazine exhibits basic properties because of its lone pair of electrons on each nitrogen atom. Many of its reactions are analogous to those of ammonia. Anhydrous hydrazine undergoes self-ionization to a small extent, yielding hydrazinium, hydrazide, and hydrazide species. The magnitude of K value for this self-ionization in the order of 10 to 25, which is greater than that for anhydrous ammonia ionizing to ammonium and amide ions. Anhydrous hydrazine thus forms salts with halide and other anions of the composition, which of acids. Similarly, metallic hydroxides are bases in anhydrous hydrazine. Most hydrazine salts are unstable and are sensitive to heat and shock. Then I explain reaction with sodium metal. Reaction with sodium metal yields sodium hydrazide. Reaction with sodium amide also yields the same compounds with liberation of ammonia, hydrazide salt of alkaline earth metals such as and of aluminum. Aluminum are known and are less sensitive to heat and shock than our alkali metal hydroxides. Reaction with alkali and alkaline earth metal hydrides also produce the same ionic metallic hydroxides. Many metal alkyls undergo similar reaction forming their metal hydroxides. Reaction with benzoic acid. A reaction with benzoic acid yields benzyl hydrazide. The product hydrazide may be sulfonated and decomposed by heating with a base in ethylene glycol to yield benzyl dehyde. Many aromatic aldehydes may be produced by similar routes. The hydrazone derivative of tolo sulfonic acid react with an aldehyde or a ketone in the presence of a base catalyst such as sodium ethoxide to yield the corresponding olefin. Reaction with sulfonyl chloride in the presence of ammonia yields sulfonic acid hydroxides. And the last one I discussed in potassium azide in front of you. Potassium can be produced by thermal decomposition of potassium azide. High purity metal may be produced by distillation of technical grade metal. Potassium may be packed undergo nitrogen. Argon should be used for packing high purity metal. Metals are shipped in stainless steel or carbon containers. In small quantity, potassium is transported in glass or metal ampoules. If you have any question, thank you so much.